Greetings and welcome to the third day of our Research in Options meeting. And today we are going to start with a talk by Professor Ernst Eberlein from the University of Freiburg. He's going to tell us about a multiple curve Lévy swap market model. Professor Ernest, it's really a pleasure to have you here, and we look forward to your presentation.
Yeah, thank you, George, and hi to everybody who is listening to this talk. Before I dive into multiple curves again and swap rates, I want to say two things. First of all, I want to send my happy greetings and happy wishes to Marco for his birthday. Many happy returns. Unfortunately, this year we cannot raise a glass, but I hope there is a chance to meet again next year in person, and maybe then there is a chance to raise a glass. And the second thing I want to mention is this book. I announced it a year ago in Rio. It actually appeared 2 weeks later, so those who had pre-ordered at a special rate got it on their Christmas table. It's 770 pages. It develops mathematical finance from a semi-martingale perspective, of course with special emphasis on Lévy processes and more general affine processes. So if you're interested in models on this mathematical level, it might be a reasonable source. Now, this project on swap market models in the multiple curve context is a joint project with Christoph Gerhardt and Eva Lütgeboomert. Christoph went some time ago to industry. I hope he's listening to this talk. And Eva is heading the quantitative finance group in the economic school at our university here in Freiburg. Let me show you this famous picture, which marks here the beginning of the financial crisis in the beginning of August 2007. The market realized at that time that the interbank market is no longer risk-free, that there is risk in this market, and as a consequence, these spreads showed up and they never disappeared. Now, the proof for the riskiness of this market was delivered roughly 1 year later, where this peak is shown in the picture when Lehman Brothers collapsed on September 15 in 2008. Now, here is the famous euro crisis related to Greece. What does it show? It shows that the tenor of an investment matters. In a risk-free world, it's not making any difference to invest your money for 6 months compared to 2 times 3 months. Because after 3 months, you invest in the same thing. But if there is risk in the market, it matters. You are free to choose a new investment partner after 3 months. And this translates into a risk premium, which are these spreads, which we see here. Another way to look at it is to look at the discount curves. Here we have discount curves from 2006, 2008, 2010, 2012, 2014, 2016, and you see how these discount curves, which correspond to specific tenors. Here it's the overnight rate, the 1 month, the 3 months, the 6 months, and the 1 year rate. These rates drifted apart, and that's the situation until now. And as a consequence, the classical single curve models do not work anymore. Here is a small selection of all the papers which were written in the meanwhile on multiple curve modeling. In developing models for interest rate, one has considerable freedom to choose the basic quantities whose dynamics are specified. So this modeling task started with relatively simple short rate models at the beginning. Most of the papers which are in this list consider the instantaneous forward rate, in other words, the Heath-Cherrow-Morton approach. This includes, for example, this paper with Christoph from 2018. Some other papers go immediately to the LIBOR market approach, and this can be developed in multiple curves as well. What I'm going to discuss now is a completely different approach. We look at the swap rates. There are a number of reasons why considering swap rates is attractive. Now, first of all, this choice is natural because of the availability of reliable market data. The swap market is a very liquid market, so it generates a lot of reliable data. And another reason which I want to mention is that we will later use swaption prices for calibration. And if you use the swap rate as a basic ingredient, then there is a convenient formula where the swap rate goes directly into the pricing formula. Now let me set the stage. Let me recall what a forward rate agreement is. It's a contract which fixes a certain rate for a future time interval from t to t plus delta, and the payoff at maturity then is just the difference between the rate which is observed at the beginning of this period minus the fixed rate. Of course, we have always annualized rates, so you have to multiply with the year fraction and with the notional amount, which we will choose in the following, always n equal 1, because it's just a factor which goes in. Such a contract is easy to value. Namely, if you take the forward measure corresponding to the maturity date, then you have just to take expectation of this quantity under this forward measure, and you discount with the risk-weighted bond price. And actually, this valuation formula has become the new standard for the risky interbank rates. So we have this expectation as the new rate corresponding to a certain tenor delta. Instead of considering now just forward rate agreements, we consider swaps, which is nothing but a sequence of such forward rate agreements along a fixed tenor structure, T0 up to Tn. Let's consider, for example, a 6 months tenor. Then we look at 6 months, 12 months, 18 months, etc., maybe up to 10 years. And we fix now a rate S, so the cash flow at each tenor time point is given as before by the forward rate agreement. The time t value for a time point before the start of the swap is nothing but the sum of these values, which we derived on the page before. And the swap rate is now nothing but the rate which makes this value 0. So put a 0 on the left side and solve for S, then you get this fraction. And the The numerator here will become a key quantity in the following. We consider now not a single swap, but given such a tenor structure, we consider swaps which start at each tenor time point Ti with the same maturity Tn. So this gives a sequence of swap rates. In other words, we get a term structure of swap rates. Let us play with this formula a bit to see what we really got. We subtract from the rate L a fixed rate K prime. In order to get equality again, we have to add it again. And now we divide by the same quantity. And what we see is the first summed here is nothing but a sum of values of forward rate agreements. Here, what remains is a K prime. So the new quantity which comes in is this value of a forward rate. Yes. Is this value of a forward rate? I have an echo here. Sorry, I have an echo here. Can you take care of that? Yeah, okay. So this is a risky rate. Now, if we take the overnight index swap, the OIS rate, then we have the classical relation 1 plus delta LIBOR is just the quotient of the riskless bond prices. If you plug it in here, you see that in the numerator, we get just a telescoping sum, and what remains is the first term and the last term. And this is, of course, the classical formula for the swap rate, which was valid in the risk-neutral world. If you compare these two formulas, we see that in addition to riskless, risk-free bond prices, we need forward rate agreements. And this is the basic thing which I'm going to do now. We consider a market which has these two basic assets, OIS, zero coupon bonds for all maturities, and forward rate agreements for the tenors which we want to consider. This is 1 week, 1 month, 3 months, 6 months, etc., up to 1 year typically. Now let me say immediately that we do not have to consider all strikes. It's sufficient to consider some fixed strike K prime because the value of the forward rate agreement for any other strike K is related to that fixed strike K prime via a simple formula. As I said, these sums which we saw play now a key role as a numeraire, as the discount factor. The key technical tool which comes in here is the forward swap measure. You might be familiar with a forward measure where you discount just by the corresponding bond price. Here it's a bit more sophisticated. For the forward swap measure, we discount by delta times the sum of the bond prices from the beginning, Ti to Tn. And by definition, the forward swap measure is the measure which makes the traded instruments, these are the two, the bond prices and the forward rate agreements, discounted in this way local martingales for all strikes and for all instruments which are in the market. This is how it looks like if we look at the most distant swap rate. And the most distant swap rate, we do not have a sum, we have just the bond price Tn. And if you look at the formula which I derived before, the swap rate corresponding to time point tn minus 1 can be represented in this way. And this quantity, this quotient, by the very definition of the swap measure, is a martingale. Adding a constant does not change anything. So the swap rate, by definition, has to be defined under the corresponding swap measure as a local martingale. So this is how we do it. We have a certain starting value, which for this most distant rate is nothing but L, the LIBOR, for this tenor. And we model it with a time inhomogeneous Lévy process as driver. So here is the canonical representation. We have a continuous part, we have a pure jump part, and we take the exponential of the stochastic integral given a certain volatility function. Typically, we take Wasicek volatility. We will always take, to make life a bit easier, deterministic volatility functions, and we integrate it with respect to this driving process. So this is the random term in the exponent. Then we have a certain drift term. We don't need a drift for the LIBOR, for the driving Lévy process, because here comes an extra drift. And now we have to make certain assumptions, which I did not write down in detail here. We want to get a martingale. And to make sure that exponential of this stochastic integral makes sense, it has to have a finite expectation. We have to assume that the driving process has exponential moments and the volatility function is bounded. Now, of course, it's always bounded. And then it is clear that this quantity, once we choose the drift term appropriately, can be made a martingale. And what is the appropriate choice? The appropriate choice is we need the compensator of the Gaussian part, that's here, and the exponential compensator of the pure jump part. Forget about the minus signs here in front, they just mean that you divide by it. Now we need that standard result, which is already in our 99 paper with Sebastian Reible. If you take the expectation of such a stochastic integral, it can be represented via the moment generating function, and these are the components which you need. So if we specify the drift according to this formula, we get a priori a local martingale, but it is, at least in this first step of the backward instruction, easy to see that it is a true martingale, because a two-line proof shows once you have exp of such a process with independent increments, as long as we have a deterministic volatility, this is still a process with independent increments. You divide it by its expectation, this is a true martingale. We do the same thing for the risk-free part. Now here we have a simpler formula. The argument is exactly the same. We have here the difference of a local martingale minus 1, and that means we are forced to define the forward OIS rate again as a local martingale with another volatility function. We choose again the drift corresponding to the input here, and then with the same argument you see it's a true martingale. And of course, this ordinary exponential can easily be written as a stochastic exponential or equivalently as a stochastic differential equation. We will need this in a few minutes. Let me have a quick look at the next step of this backward induction. The backward induction is similar to the famous BGM, the Leiber-Markov model, we start at the most distant one. Though this is the second rate now, and this is the representation which I derived before. The numeraire is now a sum with two bond prices. The same holds true for the riskless rate. We can already divide here by the numeraire for the Tn swap measure, and you see what we get under Tn is a quantity which consists of martingales. Here is this quotient, and since it's a local martingale, it can be expressed under Tn with the Brownian motion corresponding to Tn and the compensator which corresponds to Tn. We do not know so far what these coefficients phi and psi are, but we will derive them. The same can be done for this discounted quantity. We get another equation due to the representation property. Let me have a look at the measure change. We started out with the forward measure, the swap forward measure, which is nothing but the forward measure itself, because up to this factor delta, the discount factor is exactly the same. Now the density is nothing but the quotient built from the two numeraires multiplied with a normalization factor. And if you look at this quantity, just take the quotient here, it's nothing but this process ZD. This is a 1 here, so we can easily write the dynamics down, and we represent this density as the stochastic exponential of the stochastic logarithm. So this is the stochastic logarithm by definition. This means it can be represented according to this equation via the process ZD. That means we need the coefficients of ZD later. And now, since we have an explicit expression for the density, Girsanov comes in, we get a new Brownian motion, and we get a new compensator. And we use this now to build a new driving process under the measure which corresponds to the time point Tn minus 1. We define the swap rate using this new process with a new volatility function. We determine the drift as we did before. Here are the starting points. So we can again secure that this is a local martingale. Now in this second step already, it's a bit more work to show that this is a true martingale. We want to have true martingales because we want to have the densities to be true martingale. And this is closely related to the density process. For this purpose, one can use a big variety of criteria which have been developed. One of the standard references is this paper by Carlson and Sheyayev from 2002. Actually, we do not use this one. We use a paper which builds on that, which is by David Greens, Katrin Glau, and Sorana Gerbach. So they have a nice criterion by which we can make sure that this is not only a local martingale, that is a true martingale. It's always about integrability. The difference between a local martingale and martingale is nothing but the integrability condition. This can be secured here. And we can represent also these rates now as stochastic exponentials, which means as stochastic differential equations. And in this case, we have a simple relation between the discounted quantities and the swap rate itself. So the dynamics of these two is the same because they differ just by a constant. And then we can compare the two representations in terms of stochastic differential equations. And that is how we get these so far unknown coefficients phi and psi, because with this comparison they can be expressed in terms of things we know, namely the volatilities and the swap rates. And now you continue to develop this in a backward way up to the beginning of the term structure. As a consequence, we get each of the swap rates in the same analytic form, and the price we pay for this is that we have to switch from one swap forward measure to the next one. Now, as I said, one of the reasons to develop such an approach is the swoption formula, because if you express it in terms of the swap measures, it's a very simple formula. You have just the usual call payoff here, and this quantity can be evaluated using Fourier techniques. In the implementation, we use purely discontinuous Lévy processes, namely generalized hyperbolic processes. The Gaussian part would not really improve the result. The input, this is given by writing the moment generating function down. We have to use the compensator in an approximative form, namely we have to freeze the terms. That's similar to BGM in the Leiber model. And then we get a nice expression for this. And here is the other input, namely the Fourier transform of the payoff function. And as a result, we get a nice Swoption formula. That's an integral formula, which can be very efficiently be evaluated. Here is the result of the calibration exercise. These are the four parameters of the generalized hyperbolic Lévy motion, which drives the whole construction. The fifth parameter, the mu, does not play any role for the valuation formula. And here are the parameters for the Vasicek volatility functions, which go in. And here I can show you a graph. The blue triangles are the data points from the market, the prices, the swoption prices, and the red points are the calibrated values. Actually, one gets the impression that here is a big difference, but it isn't. So the differences are in the order of magnitude 10 to the minus 3. And this is what I wanted to show you. It is important that it is possible to implement it in this degree of generality. This is a preprint which is currently under revision. Thank you.
Thank you very much, Ernest, for this very interesting and very deep talk. This is a particularly important subject for people all over the world, in particular for Brazil, where the fixed income markets are extremely important. So I'd like to start, before we see some questions there, with a simple question. At about slide 11 or 10, if I remember it correctly, you had some assumption about the volatility. And if I remember it correctly, you said that the volatility, you're assuming the volatility would be constant.
No. It's deterministic. Maybe I said constant, but
deterministic, yeah.
It's deterministic. Also, typically, we take Vasicek volatilities.
Right. So what happens if it's not deterministic, if you have random volatility?
Yeah, then the analysis becomes even more involved because, of course, this stochastic integral here in the first step is still a process with independent increments. Now, in the following steps, you lose independence anyhow, but the analysis would become somewhat more involved. I admit this, but it is possible.
I see. Yeah, there is a question here from the audience, which I'm not totally sure I understand, but I'll try to relate to you. Perhaps you'll be able to make sense. How does the density parcel interfere in the equation in terms of analysis?
Could you read it again? How does the density?
Parcel, perhaps there was a typo there, interfere in the equation in terms of the
Here is the density. Is the question related to that slide?
I'm not sure.
I mean,
Well,
the density is closely related to the swap rate up to some factors and some constants. And this is why we force the swap rate to be true martingales, because the density, of course, has to be a true martingale.
right. Okay, very good. Very good. All right. So with that, I think we can say thank you again to Professor Ernst Eberlein for this very nice talk.